Okay, so let us start. So very good afternoon to one and all. Uh, so we will start today session. So very good afternoon to one and all. Welcome you all on this NPTEL online certification course on mass transfer operations. So quick view. So this course has been offered by Professor Vishnu Mandal from the Department of Chemical Engineering at Institute of Technology, Guwahati. And a little bit about myself is that I will be the teaching assistant for this course during the entire session of the course, that is from July to October. They will be taking all the interactive live sessions, that is on every weekend from Saturday from 3 to 4 p.m. And I'm Rashmi Shubham Ajikumar, and PMR Scholar in the Department of Chemical Engineering at IIT Madras. Okay, so like from the week 5, from the week 0 to from the dry run to the week 1, 2, 3, 4, 5, we have gone through some of the basic fundamental concepts of the mass transfer operation once, which is generally considered to be as the main core course of the chemical engineers. So today what we'll do is that we'll go through some of the other concepts related to the absorptions, distillations columns, and some sort of the gas absorption columns, because last week we studied related to the towers like pack towers, tray towers, and how this different terms are related to each other, like the dumping, weeping, coning, entailment, flooding, and what are weirs, downcomers, and that's all. So last week what we did is that we went to another module of the course which related to the towers and the designing of that one. And this week includes a little bit about of the introduction of the gas introduction to absorption, that is the gas absorption columns and equilibrium gas liquid system and minimum liquid rate transfer. The other term is the design of the pack column absorber based on the individual mass transfer coefficient. The third one is design of the uh, pack column absorber based on the overall mass transfer coefficient. So last week we have derived a relation between the, and earlier we already derived the relations between the individual and the overall mass transfer coefficient, that is capital, that has been represented by capital and the small k. So if you consider capital, it will be the overall, so capital X and capital Y, and small kx and small ky. So you can consider this as overall mass transfer coefficients and individual mass transfer coefficients. So these two are the things that we are going to already covered up. So like I start the absorption term here. So what is absorption for this week? As you've gone through the lecture notes, you might heard of this absorption. So gas absorption is dissolving one or more components actually. So gas absorption is dissolving one or more components of the gas into the liquid system. Into a liquid system, and to provide a ultimately a solution. So this is the one of the basic definitions of absorption, and examples are just quickly as absorption of ammonia or gas from byproduct coke oven gas, or absorption of ammonia into water, and so on. Okay, so this is like some of the like other gases can also removal of H2S from natural gas can be the other example. Removal of hydrogen sulfide from natural gas. So all of this can be done with the help of using some of the solvents or the internals, and absorption can occur via two processes. So we'll say absorption occurs via, there are two different types. One is chemical, another one is physical. And there are various examples for both of them. Like for the chemical absorption, we can consider an example of chemical reaction between a CO2 and amine solution, whereas for the physical absorption we can consider oxygen present in the air dissolves in the water. So these are some of the examples. And absorption requires mass transfer of the substance that from the gas phase to the liquid phase. So there is the transfer of mass occurs from the gas phase to the liquid phase in terms of gas liquid absorption. When mass transfer occurs in the opposite direction, it is called desorption or stripping. So the opposite term for mass transfer is desorption. Opposite of absorption is desorption or stripping. Okay, so these are some of the very different terms related to the absorption and what is different terms related to the stripping. So like I said, if you consider as a system, or system consists of more than one components. So if you can multi-component system or a binary system, in binary system there will be two different components. So the various systems will have very different parameters to study. Like if you have gone to the lecture notes, there will be equilibrium solubility curve, equilibrium curve for the same things. And for the multi-components also, there have been derived the same thing also there. So what I will do is that I will not go into the detailed analysis section, but I will show what is this like how to selectively absorb a particular gas into the liquid. So if you have seen this I have taken from the lecture notes, this image, and it shows the minimum liquid rate required for an absorption, means the mass transfer required for an absorption column. So you can see this is an absorption column as mentioned here. So this is taken from the NPTEL class notes itself in order to explain, just to pick the view what is absorption column and how the mass transfer is being carried out. So in order to selectively absorb a gas into the liquid, we require selectivity of the solvent. So the first thing that depends on the solubility. So the solvent in which the solubility of the solute is high is a preferred solvent actually. Okay, and the second thing is that we need to mention is that what volatility. So the first one is selectivity, another one is volatility, third one is the cost of the solvent included. It should not be very expensive, it should be economically feasible, and it should be corrosiveness. It should not be corrosive, because if the solvent is corrosive, it will corrode the components of the gas absorption column, which will actually increase the capital cost or the per capita cost of the like operation cost of the column. Fifth one is viscosity. Ideally, low viscosity is preferred so that it flows easily. Low pressure drops on pumping and improved flooding, and good heat transfer characteristics will be applicable for the gas absorption columns. It is having the low viscosity. And the hazardous and the viscosity. Hazards, viscosity we already discussed, so we'll discuss about the toxicity. So the solvent should not be hazardous or should be toxic, because if it is that, is definitely going to affect the environmental relation problems, also with the persons and human beings working with them. So it should ideally prefer that the solvent should be non-hazardous, should not be hazardous or toxic. It should be preferably non-flammable. So these are some of the in the image we have carried out the mass transfer exam gas substitution column, in which we have shown the gas entrance at one point. As you can see, this is the gas entrance here, this is the in, and this is out. Oh sorry, this is in actually. this is gas inlet, and this is gas outlet. Similarly, this is liquid inlet, and this is liquid outlet. So this is gas, gas. So you can see the gas and the liquid are flowing in the opposite direction. So this is liquid and this is gas. So both are flowing in the opposite direction. So this is known as a counter current mode in order to effectively absorb the gas into the liquid solvent. Okay, so this is one of the form, and all this mentioned as G1, G2, what is G1, G2, what is GS has been mentioned in the equations that you already derived. So if you carried out the overall material balance, the overall material balance is given as GS Y1 minus Y2 equal to LS X1 minus S2. So X1 and X2 are the mole fraction components in the liquid, and Y1 are the mole fraction components in the gaseous form. And GS and LS are the you can say is the rate of the gas flow or the liquid flow on the solid flow basis in mole per time. So this is one of the form, and therefore on rearranging the above equation we can get that LS by GS equal to Y1 minus Y2 divided by X1 minus X2. Okay, so this is one of the form of the equation which, if you have gone through the lecture notes, this is one of the form in order to determine the gas absorption column relation between the gas and the liquid flow rates. Similarly, there are so many terms and the concepts related to the figures. We are not going to that too in the deep in the details because we need to solve some of the problems also. So what we'll do is that we'll see how to get the minimum rate for the. So this is what the actual thing. So if in the examinations, if they ask what is the minimum liquid rate required for the absorption, so the main thing is this thing. So there will be a minimum liquid rate which is required for the absorption. So the minimum liquid rate can also be determined by a similar graphical construction on the xy plane using the mole fraction units of the concentration. So if I can say directly from the point of view on the xy plane, and if I've gone to the notes, there is a formula which relates minimum liquid flow rate required, that is LS minimum equal to GS Y1 minus Y2 whole divided by y1 by alpha minus x2. So this is the it can be noted in any particular problem. It is typically termed as a pinch point actually. So you can see if the in the equilibrium relation expressed in the terms of the mole ratio units, the linear term, that is y equal to x, that is y. If we can express y is directly proportional to x, so you can define y is directly proportional, y is equal to alpha x. The minimum liquid rate can be determined algebraically by calculating the x max, that is the maximum concentration of the liquid mole fraction components of the liquid, that is y1 by alpha, by substituting into the material balance equation. So this is what we get. So if you consider y is equal to alpha x, therefore capital X is equal to y by alpha x max. Okay, so this is another form, like how to derive at a particular point. So there are some different terms that you need to take care before arriving at this point. So what is that is an absorption tower has to be operated at a liquid rate larger than that is no minimum. There is no general rule for determining the actual liquid rate to be used, but the factor that govern the choice of the liquid rate will be discussed in the later course of the course duration. However, a liquid rate of predominantly which what has been reported in the literature is 1.2 to 2 times the minimum is frequently used actually. So in this connection, it will be interesting to have a closer look at the shape of the equilibrium line in connection with the determination of the minimum solvent rate for the gas absorption. So it all depends on how the equilibrium line and the y equal to x line is related to each other, and what is the minimum solvent required for the same. So if we have already gone to the Henry's laws and Raoult's law for the same thing. So if Henry's law, that is y equal to mx, that is for the straight line equation, is applicable, and if m is greater than 1, the equilibrium line on the xy plane is concave upwards, and the pinch points corresponding to the minimum solvent rate of absorption occurs at the bottom of the tower. On the other hand, if m is less than 1, the xy line is concave downwards. Okay, so these two are the main different things you need to remember actually. So right now we will solve one question, and this is I already included from the lecture notes. So what I've seen is that what I've given is that a gas mixture containing 3% by volume pentane vapor and 90% inert. The mixture is heated to a non-volatile is treated with a non-volatile absorption oil in an absorber with 97% and 97% removal of the pentane is required. So the gas minimum required is 97%, and the 3% must be the outlet should contain 3% of the pentane, that is the 97% has to be absorbed in the solvent. The feed solvent is free from the solute and the feed gas rate is 50 kmol per hour. The equilibrium relation is given as y equal to m. M is given as 0.25x plus divided by 1.75x. Calculate the minimum solvent rate required. So just we type, so we have given gas rate equal to 50 kmol per hour and y1 equal to 0.03 mole fraction. Input rate of pentane equal to 50 into 0.03 equal to 1.5 kilomole per hour. Carrier gas concentration in, that is 50 minus 1.5, that is what we got as a carrier gas concentration due to the inlet. So we have given is that 90% of the solute has to be absorbed and only 3% the carrier gas. Therefore, if you calculate mole fraction y1 is equal to small y1 divided by 1 minus small y1, this comes out to be 0.03 divided by 1 minus 0.03 equal to 0.03 divided by 0.97 equal to 0.0309. Similarly, capital Y2 equal to 0.03 into capital Y1 is equal to 0.03 into 0.0309, this comes out to be 0.009. Also, we have given that the solvent is free from the solute, so X2 is 0. So its solvent does not contain any solute. Therefore, if you consider plotting the x equal to y diagram, so what you have to do is to plot an x versus x will be here and y will be here, and if you plot the relation, plot the equilibrium data on xy plane and locate x2 and y2, so we have been given equation as capital Y is equal to 0.25x divided by 1 plus 0.75x. So using this equation, you have to plot the y equal to x line. We will be getting some line like this, and like this somewhat. At the point where there is an intersection, you have to locate point x2 and y2, that is this and this. Okay, and draw the operating line through x2 and y2 that touches the equilibrium line. So the point of tangency P is the pinch point, and the operating line corresponds to the minimum liquid rate. So the slope of the operating line is so you can, from the graph, if you plot the slope of the operating line, you will get ls minimum by gs equal to 0.019 minus 0.009 divided by 0.08 minus 0 is equal to 0.125. Therefore, less minimum solvent rate required is gs is given as 48.5 into 0.125 equal to 6.06 kilomole per hour. Okay, so this is how you can derive the minimum solvent rate required for the thing. Okay, so this is one of the basic fundamental concepts that you need to take care of while deriving some of the equations and tech tower. The another thing that we have gone is the pack tower design. The another concept that has been discussed during the district is uh, pack tower design. And the similarly pack tower design and the various concepts like the pack tower sizing of the pack columns basically includes, there are different parameters need to take care of. So so the first thing for the following, if you can say, the following items and variables should be known for the designing purpose. So for the first thing is equilibrium data. Second one is flow rates, and terminal concentration of the gas and liquid phases. Third is the individual or overall volumetric mass transfer coefficient, also called as capacity coefficient sometimes. Okay, so similarly you can design the pack tower also, and there are different terms and different parameters you need to take care of while designing the pack tower also. Similarly, I'm not going for the deep concepts because if you try to solve out each and everything, we'll not be able to solve some of the fundamental questions here that we are trying to carry out forward. So what I will suggest is that go through the questions, try to learn out and see what you can grab from that concepts. So what I will doing is that just covering the basic concepts like various things that has been went to the design of the pack tower and the overall mass transfer coefficients for the same. So also there is another one concept for designing the, for determining the number of the pleats required or the number of stages or the height required for the packing tower, as ZTG, number of gas phase transfer, number of liquid phase for mass transfer units, and the overall height of the pack tower required for the same. So that also can also be derived using the same concepts, but the only thing is that it says the formula of design based on height of transfer unit. So this is what is called as HTU, and if you have seen this formula, Z equal to HTG and to NTG. So this is the Z is the height of the transfer units, and HTG is the height of the transparent, and number of transparent is the total height of the column. And also in terms of this can also be written out HTL into NPTEL. Okay, so these are general writing the final equations where HTL is the height of an individual liquid phase mass transfer liquid phase transfer unit, and NTL is the number of individual liquid phase transfer units. So there are different formulas for the same also. You must go through all the derivations that has been mentioned in the lecture note, because there is a deep fundamental derivations. If you go through the lecture notes, it will be better for you guys to understand all these things, because if I try to solve all these equations here, it doesn't make any sense right now. It's a point of view. So what I suggest, just go through the lecture notes and let me know if you face any difficulties in the derivations. From next week, what we'll do, we will try to solve some of the basic fundamental uh, directly the numerical problems based on the derivations. This week I am not doing any derivations in this class, because you need to learn some of the basic terms related prior deriving that derivations. Okay, so it's better to go through the lecture notes and see if you guys face any problem related to the concepts and the derivations. Please let me know. I will happy to solve it out. In this class, I'm just showing you some of the basic concepts related to the designing of the absorption columns. What should be considered regarding the selectivity, volatility, toxicity, and some of the basic formulas for that. So apart from, on the basis of that, I have given some of the answer cues. So if you can go through some of the things that are given up here. So if you see, what I mentioned is that the first question uh, and the second one. So if you can see in the first question, the processes where absorption of gas finds application are. So absorption can be find application in almost all the chemical industries, and on the basis of the options mentioned here, that is first one is production of sulfuric acid and oleum, hydrochloric acid production, and nitric acid production. So yeah, as far as industries are concerned, absorption is one of the basic, like the deep operation that has been concerned in many processes, and all of the options are correct for this, and its absorption has been carried out in almost all of the cases of the mentioned concepts here in the options. The second question relates what is absorption. So absorption is favored at high temperature, favored at low temperature, independent of the temperature, or none of the above. So usually absorption isn't favored with respect to the temperature. Absorption is a temperature dependent formula, temperature dependent concept. uh, and by going to the like basic fundamental concepts of the absorption, it relates that absorption is a favored by the low temperature. So this one you should know while deriving the some of the concepts or some of the numericals. You will see the temperature mentioned that in the absorption will be low as compared to some other processes, like some other operations are compared to distillation operation and extraction and also. So this guys you should remember from the day one itself, because this carries also like 1 to 2 marks in the final examination if they ask the same question. Okay, so now the second one. So pick the correct statement for the selectivity. Pick the correct statement for the selectivity of selection of solvent for absorption. So I think you are able to. Okay, it's lagging. Now it can see. So this is another question third and question four. So pick the correct statement for the selection of the solvent for absorption. Like I said, the solvent should have a high volatility, high viscosity. Solvent should be highly soluble in the solvent, or the solution should be corrosive. So like I said, the solvent that is used for the absorption should have low volatility. First of all, so this one is not correct. It should have low viscosity. First of all, this is mentioned as high viscosity. The another thing that I mentioned is that it should be non-corrosive. So here it is non-corrosive and non-toxic. The another thing that we already seen is that it should be highly soluble. Once it is highly soluble, then only it can absorb much of the gas into the heat. So the correct option is the C1. Similarly, at pinch point, the driving force. The pinch point is the point at which the equilibrium collides with the equilibrium point, that is phi equal to x. So the pinch point, the driving force is zero actually, and we can determine the x2 and y2 points, and from that we can find out the things very easily. So this is pinch point, which I have just not covered in the today's concept, but I just shown you the plot from the y equal to x and when these 2 points collides, if you consider this as a Poch point, and you can consider in the y equal to x formula, and you can determine the values of the equilibrium curves. So this is at pinch point, the driving force is 0. Okay, so this is what I have for today, because today we didn't cover too much, but what I like you guys to go is that, because this week is much more for the derivations of the uh, derivation in the term of the sense of what you can say, like the sum of a pack column, as well as the concepts related to that. But what I will suggest is that from next week we'll solve some of the lengthy numericals that has been given in the assignments also, and plus we will go to some of the MCQs and the concepts related for the same. So I thank you guys. Thank you guys for joining this class. We'll meet next week. Thank you guys. If you have any problem, just post in the NPTEL Swim portal, or you can also drop a mail for the same. Please let me know. We will happy to sort you out for the same things. Thank you guys.